So what we're going to do is we're going to make x slowly get larger and larger. So we're going to start by plugging in 100 and then 1000 and then 10,000, 100,000 and so on and so forth. And you can see there is a number or a value that it's getting closer and closer to. It kind of stops getting larger and it approaches and gets close to around 2.71828. And that is actually how we generate the value of the base e. So think of e as an irrational number and it's a constant, just like pi. Now, what the function of e to the x looks like, it's similar to the exponential function. So it's just a special case of an exponential function with a base of e, or around 2.7. And when we plug in or substitute some values into the function e to the x, it slowly gets larger and larger, and the function or the graph would look something like this. So when are we going to use that e? Okay, we're going to start with what we call computing compound interest. So the formula to do that is a of t is going to equal p, which is the initial amount, p or the principal amount that you invest, times the parentheses 1 plus r over n raised to the n times t. So if you notice, this is similar to the exponential growth function, but instead the rate is being divided by the number of compoundings per year, and the exponent is being multiplied by that as well. So notice that the n is going to be affecting the whole thing. So what happens is, for infinite compounding, so per year it could be twice a year, 3 times a year, quarterly, which means 4 times a year. It could also be once a month, so that would be 12 times a year. And if you keep doing that, make the number of n larger and larger and larger, that parentheses right there, the one inside the parentheses, looks a lot very similar to the value of e when we make that x larger and larger and larger. So when we are compounding continuously, we use a different formula in the form of a of t equals p times e to the rt.